Welcome to the lecture number 56. From today, we are going to begin very important chapter called circle. You will find this chapter is very important from examination point of view. Reason being that it is a largest chapter in the textbook. Secondly, there are so many theorems in this chapter, and all the concepts are keep on varying. So, if we sum up all these points, you will surely find that this importance of this chapter. Now, there are minimum 7 to 8 theorems are there, and very frequently those theorems are asked in the examination, in SSC examination. Weightage is also very big. So, please focus on this chapter properly. Try to understand all the concepts. For all the time I told you that whenever theorem part is there, so remember this theorem part you have to write as it is exactly given in the textbook. That is very important. Even in this case also you will find I have taken some different alphabets than that of the textbook, but when you will write the proof, I am requesting all of you that please to write the proof exactly as given in the textbook. No matter if you change the alphabets, it's okay, but not a single line should be missed out from the textbook. Now let's begin this. You will find first theorem. But before I begin the theorem, there are some basic concepts, and all these basic concepts you all know. For example, what is meant by tangent? Tangent always touches the circle. Okay, tangent always touches the circle, or we can say intersect the circle in one and only one point. This is very important fact that we have to use over here, that tangent always touches the circle in one and only one point. Touches, or more precisely in a scientific language you should say that it intersects the circle in one and only one point. That is important thing. Secondly, what is mean by secant? Secant is any line, segment, or even chord is also called as a secant in many cases. But in general, the proper definition is secant is always a line which intersect the circle in two distinct points. Okay, that's all dear students. Now I am going to begin this important theorem which is given on page number 51. Please try to understand this theorem. A tangent at any point of a circle is perpendicular to the radius to the point of contact. That means this is a circle given. This line L is given. Line L is a tangent to the circle. If line L is a tangent to the circle, means line L will intersect the circle in one and only one point, and that is point M. That is point P. Line L will not intersect the circle in any other points than P. And we have to prove if MP is a radius. If MP is a radius, then this line L and radius NP makes an angle of 90 degrees at the point of contact. That is what we have to do. So what we have to do? Angle P is of 90 degrees. Now our supposition. I am going to prove this by indirect method. Try to understand what is meant by indirect method also. Indirect method is a method in which whatever we have to prove, our supposition is exactly opposite to that. Is in a negative sense as that of whatever we have to prove. And then we will take that supposition into the consideration, and we will go on applying theory, and finally we will reach at some conclusion where that conclusion becomes absent or meaningless, and then we will claim that this absurd result we got, reason being that our supposition was wrong, and then we will get the correct result. So this is how this indirect proof method is used. Okay. Now we have to prove that MP is perpendicular to L at point P. So our supposition is MP is not perpendicular to L at P. What is our supposition? That MP is not perpendicular to L. Okay. If it is not perpendicular at point P, then you always know that there may be at least one point. There may be at least one point at which point this line from M will be perpendicular to L, and that point we have taken it as B. But while taking point B, we have taken one more precaution, than taking point Q and P such that BQ is equal to BP. We have taken the position of Q and P such that BQ is equal to BP. Now you will find, if we consider these two triangles, then you will find NB is congruent with NB. Reason being that it's common. Then angle NBQ is congruent with NBP, each is 90. And BQ is equal to BP by construction. So this is how you will be getting triangle NBQ and triangle NBP. These two triangles are congruent. And they are congruent by SAS test. SAS test. But if these two triangles become congruent, then obviously you will find that NQ is equal to NP. It is but natural, because NQ and NP are called as corresponding sides of congruent triangles. But what is NP? NP is a radius, and radius and tangent are intersecting one and only one point. But if we got NQ is equal to NP, that means we have drawn two segments from point M, namely NP and NQ. That means P and Q are not different, but one and the same. And in case if you will say these are different, then naturally what happens? Then it happens that line L is touching to the circle in two distinct points, namely P and Q, which is absurd result. And therefore our supposition was wrong, that line L is not perpendicular at P. Then what is correct? Correct statement? Correct statement is line L is perpendicular to P if NP is a radius. If NP is a radius. Now please look at this theorem. Theorem statement is a tangent at any point of a circle is perpendicular to the radius through the point of contact. Point of contact is P. Given line L touches the circle with center M and point P. Yes, this is line L, this is a circle, M is the center of the circle. To prove that line L is perpendicular to the radius, and line L is perpendicular to the radius, and proof it is indirect method. Let us suppose line L is not perpendicular at point P. What is our supposition? L is not perpendicular at point P. That is what we say. Then line L is perpendicular at point P. You will find here students. From point M, I can draw at least one perpendicular. And if I say, if it is not perpendicular at P, then I have drawn perpendicular at point B. then at point B. Take point Q and P, take point Q and P such that PB is equal to QB. Take point P and Q such that PB is equal to these 2 points. Correct? Then you will find in triangle NBP and triangle NB. These 2 triangles. In triangle NBQ and triangle NB. NB is congruent with NB. This NB is congruent with NB. Which is common. Which is common. Angle NBQ is congruent to triangle angle NBP, which is 90. Yes, by construction only, you will find that each one of them is 90. Therefore, triangle NBQ, and triangle NBP are congruent by SAS test. Correct? By SAS test. That is what I have written over here. That triangle NBQ is congruent to triangle NBP by SAS test. Therefore, NQ is congruent to NP, corresponding sides of congruent triangles. Corresponding sides of congruent triangles. Since NP is a radius, this theory is important. Since NP is a radius, line L intersects circle in 2 points, namely P and Q. What we got now? If NQ is equal to NP, then we got a result that line L intersects the circle in 2 points P and Q, which is absent. But line L is a tangent, and tangent intersect the circle in one and only one point. That is the definition of tangent. But what result we got? That tangent is touching the circle in 2 points, which is absent. So, but line L is tangent to the circle, hence intersects only in 1 point. Our supposition is wrong. What we got a result? Our supposition is wrong. Therefore, line L is perpendicular in 1 point, and that is only 1 point P, because our supposition was L is not perpendicular at P. So please have a look at this theorem right from beginning. See, while writing the proof, very important, they'll give you the question like this. You have to draw a circle, you have to draw a line, you have to draw this figure. This given will carry some marks, to prove will carry some marks. Proof, of course, will carry marks. If this theorem comes, naturally it will carry 4 marks. So please do write this theorem. Carefully observe this theorem, write it from the textbook only. Please have a look at this theorem. Now next theorem is there. Next theorem. This theorem is given on page number 52. This theorem is given on page number. Statement of the theorem is a line perpendicular to a radius. A line perpendicular to a radius. A line perpendicular to a radius at its point on the circle is tangent to the circle is tangent to the circle. I'm going to add one more sentence which is not there. At that point, that is very important. Actually, it is not given in the statement, but I added over here. At that point. Okay. Then you will find given M is the center of a circle. M is a center of a circle. Then next to that, Mn is a radius. Mn is a radius. L is perpendicular to Mn. L is line L is perpendicular Mn, segment Mn at N. To prove line L is tangent to the circle. Line L is tangent to the circle. Is tangent to the circle. Okay. Proof. Figure is on screen. Circle is there. In this figure you will find they have drawn a tangent. This is a tangent. MNP. Okay. Fine. Now what is given here, students? What we have to do, right from the start. What we have to do line L is tangent to the circle. But at what point? N. Why at point N? Because it is perpendicular at point N. Because it is perpendicular at point N. Okay. Now we have to verify it whether it is tangent at some other point also or not, or only at point N only. Why at N? Perpendicular. Line L is perpendicular to the radius at N. So we are going to verify whether line L is tangent to the circle at any other point than N. Okay. So you will find, let us verify line L is tangent to the circle other than point N, other than point N. What is our claim? Our claim is line N is tangent to the circle at point N because it makes an angle of 90 degree at N. It is not tangent to any other point than N. Okay. But we are going to verify whether it is tangent to the point P or not. We are going to verify it. Take any point. Take any point. Take any point P on line L other than N. We are going to verify it whether line L is tangent to the circle at any other point than N, because N is okay. N at point N, it makes an angle of 90 degree with the radius. Now we are going to verify whether it is tangent at P or not. Okay. Take any point P on line L other than N. In triangle M and P, in triangle M and P, angle N is 90. Angle N is 90. It is given. Angle N is 90, it is given. Therefore, triangle NNP is a right angle triangle. Is a right angle triangle. Now you will find triangle NNP is a right angle triangle. If it is a right angle triangle, NP is hypotenuse. NP is hypotenuse. NP is a hypotenuse. And if NP is a hypotenuse, you all know the property of right angle triangle that hypotenuse is largest side. So you will get here NP is greater than MN. NP is greater than MN. But what is MN? But what is MN? MN is a radius. MN is a radius. So NP is greater than radius. Therefore, point P lies outside the circle. So what you will get? point P lies outside the circle. Finished. Because tangent and circle is having a common point. What does it mean? It means that tangent will intersect the point which is on the circle. But what we got? Point P lies outside the circle. Therefore, line L cannot be a tangent to the circle at point P. Therefore, line L is tangent to the circle, at point N only. This is very important. At point N only. So please try to understand this theorem again, dear students. This theorem states that a line perpendicular to a radius at its point on the circle is tangent to the circle at that point. So this is a circle. You will find, so MN is perpendicular to line L at point N. It is given there. M is the center of a circle, MN is the radius, line L is perpendicular to MN at N. To prove that line L is tangent to the circle at point C, I modify it a bit. At that point means at point N only, not at any other point. Okay. Now you will find, let us verify. Okay, to get you complete view, please look here. Let us verify line A is tangent to the circle other than point A. What we are going to verify? Whether it is possible to have line L tangent to the circle other than point N. M is having special property of making an angle of 90 degree with radius. That is what I am telling you. That is very important to understand. Okay. Other than point N. So take any point P on line L other than N, and therefore triangle N and P, angle N is of 90 degrees. So we are verifying now. What we are verifying? Whether line L is tangent to the circle at point P or not. Therefore, you will get triangle NP is a right angle triangle. NP is a hypotenuse. NP is a hypotenuse because it is opposite to 90. So NP is greater than NN because this is a property of right angle triangle that hypotenuse is the largest side. Or in other words, you can say hypotenuse is greater than remaining two sides. Therefore, you will be getting NP is greater than MN. But what is MN? MN is the radius, so NP is greater than radius. Therefore, point P lies outside the circle. Therefore, line L cannot be a tangent to the circle at point P. Because definition of tangent is tangent intersect the circle. That means that point is lying on the circle. And here what we got? P is outside to the circle and point. Therefore, line N is tangent to the circle and point N only. So this is a very, very important theorem. Okay, less time is left out for this lecture. So let's finish one more theorem. Then in the next period I can do. The next theorem is very, very important. And many times this theorem is asked in the examination. Very popular theorem is there. This theorem is given on page number. It is given on page number 53. And we find statement is tangent segments drawn from an external point. Tangent segments. Tangent segments drawn from an external point to a circle are points. Okay, so first of all I am going to draw a circle. Center of the circle is A. This is A. This is D. This is P. This is Q. Very important thing from examination point of view. Okay, so I am going to write for proof. Given point T, point D is an external point. Tangents dP or PD and dQ are drawn from point D. To prove that dP is congruent to dQ. Tangents drawn from the same external point to the circle are congruent. That is what we have to prove. dP is congruent with dQ. Join AQ construction. Join AP and AQ. AP and AQ. Proof. In triangle, please try to understand carefully. In triangle APD and triangle AQD, two triangles. Triangle APD and triangle AQD. Triangle APD and triangle AQD. Okay. Angle P is congruent with angle Q. It is 90. It is 90. Tangent radius theorem. Tangent radius theorem. Tangent radius theorem states that tangent is always perpendicular to the radius at its outer point. So in triangle APD and triangle AQD, AD is opposite to 90, AD is opposite to 90, AD is opposite to 90, AD is opposite to 90. Therefore, hypotenuse AD is congruent to hypotenuse AD. Common. Next to that, AP and AQ. AP is congruent with AQ. AP is congruent to AQ. Radii of same circle. Radii of same circle. Therefore, triangle APD is congruent to triangle AQD by hypotenuse side theorem. Is that clear? AD is the hypotenuse for both the triangles, which is common. Okay? Therefore, it is congruent. AP is equal to AQ, radii of the same circle. Therefore, we will find triangle APD is congruent with AQD by hypotenuse side theorem. Therefore, then very simple. DP is equal to QD. PD is congruent with QD. Corresponding sides of congruent triangles. Therefore, tangents drawn from same exterior point, drawn from same external point, are congruent. Okay, so this is how you will find this proof gets over. Okay, please have a review of this theorem again. That tangent segments drawn from an external point to a circle are congruent. From an external point means one point to the circle are congruent. We have to prove dp is equal to dq. Point D is an external point. Tangents PD and dq are drawn from point D. To prove that dp is equal to dq. Construction is then join AP and AQ. Then you will find in triangle APD and triangle AQD, these two triangles, you will surely find AD is hypotenuse, which is opposite to 90. But before that, P is equal to Q, that which is 90, because tangent radius theorem. Next to that, in triangle APD and triangle AQD, hypotenuse AD is a common. AP is equal to AQ, radii of the same circle. Next to that, triangle APD is congruent to triangle AQD by hypotenuse side theorem. Therefore, PD is equal to QD, corresponding sides of congruent triangles, and therefore tangents drawn from the same external point are congruent. So, dear students, I am going to conclude lecture number 56 here. This is very, very important theorem. In the next lecture, that is lecture number 57, I am going to begin exercise 3.1. Thanks a lot for listening this video carefully, as well as for watching this video carefully. God bless you all. Thank you.